times the gravitational acceleration. This force, whatever force this scale is providing, is pushing on us, this is our definition of weight, that force. So we're going to look at other circumstances and see what that force is. So for me, if I step on the bathroom scale, I look down and I say, oh, okay, 150 pounds. It's actually measuring a force, but the scales are calibrated, so they divided out the acceleration due to gravity. It's probably pretty rare to find a scale that reads in newtons, for instance. Those exist, and we actually have one over here that we might get to in a little bit. Okay, so that's a pretty straightforward example. But now imagine that I'm in an elevator. So the elevator has some sort of tether, something pulling it up. I've got a scale in that elevator, and there I am. So again, I still have the force of gravity acting down on me, and I still have the force of the scale acting up. So in this case, let's imagine that this elevator is moving upwards. So we have an acceleration that's upwards. We know now that the entire system, the elevator, me, the scale, we're all moving up with an acceleration a. So given Newton's first and second laws, we know that the force of the scale has to be greater than the force of gravity acting on me, because F net, we have the scale force pushing on me, gravity pulling, and this is going to be equal to my mass times this acceleration that the elevator is providing. We can solve for the force that the scale is pushing on me, and we get this equation. A is positive. So that means if my normal weight is my mass times the gravitational acceleration, I now have a weight which is greater than my normal weight. So we can put in a number. Let's say that the acceleration is plus 15 meters per second squared. G is 10 plus 15, so we get our weight is 15 times our mass. Our normal weight is 10 times our mass. It's the acceleration due to gravity times our mass. So that means that in this accelerating elevator, I have gained a factor of 1.5, of 3/2 times my weight. I'm heavier when that's happening. So let's consider the other circumstance. So here I am in my elevator again. I still have the force of gravity pulling me down. I have the force of the scale pushing me up. We're connected, but now the elevator is going downwards. So we have a downward acceleration, and in this case, so where the acceleration remains a positive number, let's choose down to be our increasing direction. So that came from saying, if this is my normal weight, I did not define that, it's a good question. My normal weight is just my mass times the acceleration due to gravity. In this case, when I'm in an elevator and I'm accelerating upwards at 5 meters per second squared, the weight that my scale reads, the force that the scale is pushing on me, is 15 times my mass. So that means that I am 1.5 times heavier in the elevator that's accelerating upwards than I am if the elevator were not accelerating at all. Is that? You can, talk to me afterwards or bring it up if you have another specific question. But in this case, remember, the force that the scale is pushing on me is what we defined as weight. It's what I'll look down in an elevator and I'm moving upwards and I look down on my bathroom scale. Instead of saying 150 pounds, it's going to say 3/2 times 150 pounds. It's going to read a larger weight because I'm accelerating upwards. So in this case, we're looking at a situation where we're accelerating downwards. We're going from floor 10 to floor 5 in this elevator. And again, we can draw, so this might be a little hard to see. We again have gravity pulling us down. The scale is pushing us back up. Whatever force is pushing us back up is our weight. That's what we've defined to be our weight. That's what we would look down at the scale, and that's the weight that we would measure. That's what we'd see. And seeing is believing. So force going up, gravity pulling us down. We know that we're accelerating downwards at the acceleration a, so it better be that our weight, the force of gravity pulling us down, is greater than the scale force pushing us back up. So let's actually compute what that is. So we have mg, again, this is the positive direction. So mg is positive minus fs, and this is equal to ma. We can solve for our weight, that's the force that the scale is pushing on us, and we get m times g minus a. So just as advertised, if we are moving downward, accelerating downward at 5 meters per second squared, the acceleration due to gravity is 10 meters per second squared. If we're moving downward at 5 meters per second squared, we have 10 minus 5, and our weight will be 5 meters per second squared times our mass. Again, our normal weight is 10 meters per second times our mass. So we have lost weight. The scale will read a weight that is less than our normal weight when we are not accelerating. So what happens if I cut this cable? What is our acceleration then? I heard, what is it? 9.8, 10 meters per second squared. We're accelerating at the gravitational acceleration. We're accelerating at g. If this acceleration is equal to g, what is our weight? So when a is equal to g, the force of the scale acting back up on us is 0. We are weightless. That's it. We're floating. There is no force of the scale acting on our feet anymore. If we had a cup of water, if I took my coffee here and I turned it upside down, everything in this elevator is all moving at exactly the same speed. It would not fall out of the cup. It would just stay there. It's the same types of things that you've seen in Apollo 13 or in any other movie of what happens when you're in the space station or a shuttle orbiting the Earth. This is what we mean by weightless, when you are in free fall. And we sometimes experience that if we jump off of some object like a ledge to get down to the ground, or we're playing in jungle gyms and we let go of the bars or something like that, we are in free fall. And at that point, you are weightless. And that is because the value of the force of the scale pushing back up on you, we have defined that to be our weight. That is what we mean by weight. Are there any questions? So I want to suggest another way that we can measure weight. And that is, instead of standing on a scale and having the scale push up on us, what's going to happen if, let me see if I can, oh, I'm not getting that. Okay. What's going to happen if instead we're hanging from a string? So now we're going to use string tension as a measure of our weight. So we can imagine placing a spring scale, and connect it to our string. And depending on how much that string is stretched, we can measure the tension in the string. So here I am again, and now I'm holding on to this string. So now what does my force diagram, my free body diagram, look like? Originally, when I was weighing myself with the scale, I had the scale pushing up on me. Now I still have the force of gravity pulling me down, but now I have the string tension pulling me back up. So let's do a few of the same calculations we did here, but for string tension. And then I'm going to discuss something that is surprising when we think about string tension as a measure of weight. So if we have zero acceleration, that means both these forces are balanced against each other. And that implies that the tension is just our mass times the gravitational acceleration, the force of gravity acting on us. Good, because we want to say, we're going to find that measuring our weight using tension is identical to measuring our weight using a Baffert scale. What if, instead of being at zero acceleration, we're being pulled upwards? So we're going to define this to be our positive direction. If the acceleration is positive, then again, we have t minus mg is equal to ma. So t is equal to gm times g plus a. We've seen that before. We saw that when we were thinking about the elevator and what the scale would do if the elevator were accelerating upwards. Again, accelerating upwards in the opposite direction of the force of gravity increases our weight. The tension in the string is measuring our weight. If we were to accelerate in the other direction, we can say, in one case, the acceleration is plus 5 meters per second squared. If we're going down, it's minus 5 meters per second squared. And in that case, we get the exact same relationship we did here, and we find that we've lost weight when we're accelerating in the same direction as the force of gravity. So the tension plays the exact same role. It's pulling, in this case, the scale is pushing against us, but we get the same result. Both of them measure our weight. So I'm going to now talk about an example of an object which demonstrates some interesting properties of weight. So those of you, this is a pretty delicate small thing. You can see this. It's amazing. This right here has a name, like an individual name. The Atwood machine. Tells you how important it is. It's a pulley, and you have a string that's going across the pulley, and on either side of the pulley, you have two different masses. In this case, the masses are identical, and just as you would expect, nothing is happening, because there is an equal gravitational force pulling down on one side as it is on the other. So let me show you what happens. I have an extremely small sliver of metal that I'll place on one of them, and at that point, you see that the pulley starts to move. If we leave them like this, they'll remain at rest. This is exactly what Newton's first law says. If we give them a little push, so they have a velocity, ignoring friction, which is hard to do in the real world, these actually move at a constant velocity. On the other hand, when we put an unequal mass on either side, there's a force acting on one side that's greater than the other, and they start to accelerate at a constant acceleration. So the reason why Atwood had this named after him is he invented this in order to demonstrate dynamics, in order to demonstrate Newton's three laws. We are going to use it in order to explore a bit more what it means to define the weight of an object with using tension. So from what I heard from Professor Deweese, at the end of Tuesday's lecture, he gave you guys a question. He said, okay, I have a string, and attached to this string is one mass, then I have another string, and attached to that second string, I have a second mass. And the question was, what is the tension in the top and bottom strings? I'm here to tell you, I'm not going to answer that question, I'll let you guys think about that, but I am here to tell you that strings and tension are very subtle and confusing things to think about. And I want to discuss one aspect of that with you right now in some detail. And I'm going to give you, in some textbooks you have two different tracks. On one track it's like, yeah, okay, you just accept something is true and you move on. In another track, you learn a little bit more about it because you want to know more of the details. I'm going to give you two tracks that you can follow at this point in class. And let me define exactly what I'm about to do. So let's draw this Atwood machine on the board. So we've got our pulley, and we've got two strings coming down. On one side we have mass m1, and on the other side we have mass m2. So let's call, this is very creative, let's call the left-hand side L, and the right-hand side R. So the question is, what is the tension in the string on the left-hand side and the right-hand side? I'm telling you, this is actually a hard question, and part of the reason it's hard is because we need to understand how and whether the string plays a role in the motion of this Atwood machine. So let's look. So let me actually write one more thing down that's important and introduce a bit of notation. Let's say that the string has mass m sub s. And we're going to assume, which is the case with this Atwood machine over here, that the mass of the string is much, much, much less than the mass of either m1 or m2. So that's what the symbol, if you haven't seen it before, means. This is, you read this as much, much less. It's not just less than, it is way smaller than. So let me give you a number to think about. Let's say that m1 and m2 are both about a gram. Maybe one is 1 gram, the other one is 2 grams. If I'm saying that the mass of the string is very small, I'm saying that the mass of the string is, let's say, a milligram, 1,000th the mass of either one of the other two objects. That's the reality of the situation when this is true. Physicists are going to say something different, and this is the important part. No matter whether you want track 1 or track 2, this you have to pay attention to. When this situation is true, physicists will say the string is massless. It's a very weird thing to say, because it isn't. And what if that's important? So keep this in mind. I'm going to get back to what that means in just 1 second. Let me draw a free body diagram for mass m1 and m2. So m1 has the gravitational force pulling downward with magnitude m1g, and it has the tension of the string pulling it back upwards with T sub L. Some tension. We don't know what it is yet, but there is a tension. Definitely when it's not moving, because we know the forces have to balance one another. But in the case where they are moving, things get more interesting. So when I make one mass greater than the other, you know that the two move. One of them moves up, and the other one moves down. So what is the tension on either side when that occurs? That's what we're interested in calculating. So again, we've got m2g pulling down mass 2, and we've got tr pulling it back up. So what I want to do now is focus on a very, very small bit of this string. That little bit there. So if we were looking at this guy, it would be this little bit there. So we're going to take this, and we're going to blow the picture up. So we've got our string. And let's take just a little section of that string. Let's say it's this little section here, and we'll say that this section has mass little delta m. That's what this symbol is here, a little delta. So just above this little piece of the string, there'll be a tension that's upwards, and just below, there'll be a tension that's pulling downwards. So what's the equation? We have everything we need now. We can just use Newton's second law to say how this bit of string, this small little section, is going to move. So the total net force on this small section of string is T up minus T down. And that's going to equal the little bit of mass here times the acceleration. So that acceleration is the acceleration that we see when one mass is greater than the other. So it's this acceleration here. What we're going to see in just a moment is that the acceleration of one arm versus the other is always less than the acceleration due to gravity, less than or equal to. So this allows us to say that the difference in the tension above and below this little bit of string is delta m is less than or equal to delta m times g. So now I'm going to give the answer to the track 1 people who aren't interested in necessarily looking at these details. If a physicist tells you that the mass is 0 for the string, then that means that even this little section of string is even more 0 if you can get closer to 0. If that's the case, if this delta m is 0, then you automatically know that the tension up above that little piece of string and the tension below it are equal to one another. And that tells you something very important, because you can take any other section of the string and do the exact same calculation, and you'll find that the tension is the same everywhere. So when a physicist, and I have to give you one other caveat, when a physicist says that a string is massless, they are telling you something about how the tension varies along the string. In this case, we're going to make a further simplification and say that this is a frictionless pulley. What that means is that it doesn't turn. That is not the case. I yelled at the demo people. I said, why didn't you get the right pulley? It's frictionless. They didn't listen to me. So this pulley is turning. It turns out that that makes an important difference. Well, it can make a slight difference in the equations that we're going to write down, and it's something that you may return to later when you learn about torque. There's a torque acting on that pulley up there that's causing it to spin that changes how the object moves. But we're going to ignore that. We're going to imagine that this pulley here is frictionless, so that it doesn't move, it doesn't rotate, and instead the string just slips on by. That's our assumption. When we make that assumption and say that the mass of the string is massless, it's 0, we are saying that T, the tension, is the same throughout. So for the track 1 people that just want to know, that is the key word. If you read a problem and it says a frictionless pulley or pin and a massless string, don't have to do anything more. You can write down, the tension is the same everywhere along the string. Perfect. Don't have to worry. Let me just give those who might want to know a little bit more about why that works a hint as to why it works. So I've written up there, the difference in the tension above and below this little section of string is going to be less than or equal to the mass of that little section times the gravitational acceleration. What are the other forces in this problem? This is a very common physicist trick. You want to look at quantities that have the same meaning. So in this case, this difference in tension is a force. It's telling you something about the acceleration of an object, so it's a net force. The only other forces that we have to worry about looking at the Atwood machine is the gravitational force pulling down on masses m1 and m2. So let's just pick m1 and say that they're about the same. m1 and m2 are about the same. So the only other force in the problem is the gravitational force acting on those two masses. Let's just define this to be m. Or even better than that, let's say that they are different, but we define m to be the average. m1 over m2 divided by 2. This is the only other force in the problem. So let's take a ratio, and again, this is a favorite physicist thing to do that has application to other pursuits. Take a ratio of the difference between the tension on one side of this little piece and the other to mg. Well, we know this is less than or equal to delta mg over mg. Those g's cancel out. And in reality, we know that the mass of the string is much, much less than the mass of either one of these, the two sides of our Atwood machine. So for sure, a little section is going to have a mass that's super small compared to either of the masses that we have at the ends. So this is telling us that if there is a difference in the tension along the length of the string, which there is in reality, it is going to be so much smaller than any of the other forces that we need to worry about in the problem that we can just ignore it. If we want to be very precise about what we're doing, we might have to take it into account. But for the first time we're doing a problem, this is telling us that it's a good approximation to say that Tu minus Td is 0. Or in other words, there's only one tension in that string, and we can call it T. So now what I want to do with that information, that there's only one tension, we don't have to worry about the different tension from one side of the Atwood machine to the other. Let's actually calculate the tension and the acceleration of these two masses. I wanted to say one more thing that's somewhat surprising. When we have two separate masses here, remember, I almost erased it. This tension that's in the string measures the weight. The fact that we've now decided with our approximations that the tension is the same, no matter what the masses are on either side